Welcome back. Let's read this one.
Space Shuttle Challenger disaster. Not to be confused with Space Shuttle Columbia disaster. On the 28th of January, 1986, the Space Shuttle Challenger broke apart 73 seconds into its flight, killing all 7 crew members aboard. The spacecraft disintegrated 46,000 feet, 14 kilometers, above the Atlantic Ocean, off the coast of Cape Canaveral, Florida, at 11:39 a.m. East, 16:39 UTC. It was the first fatal accident involving an American spacecraft while in flight. The mission, designated STS-51L, was the 10th flight for the orbiter and the 25th flight of the Space Shuttle fleet. The crew was scheduled to deploy a communications satellite and study Halley's Comet while they were in orbit, in addition to taking school teacher Krista McAuliffe into space under the Teacher in Space program. The latter task resulted in a higher than usual media interest in and coverage of the mission. The launch and subsequent disaster were seen live in many schools across the United States. The cause of the disaster was the failure of the primary and secondary redundant O-ring seals in a joint in the shuttle's right solid rocket booster, SRB. The record low temperatures on the morning of the launch had stiffened the rubber O-rings, reducing their ability to seal the joints. Shortly after liftoff, the seals were breached, and hot pressurized gas from within the SRB leaked through the joint and burned through the aft attachment strut connecting it to the external propellant tank, ET, then into the tank itself. The collapse of the ET's internal structures and the rotation of the SRB that followed through the shuttle stack, traveling at a speed of Mach 1.92, into a direction that allowed aerodynamic forces to tear the orbiter apart. Both SRBs detached from the now destroyed ET and continued to fly uncontrollably until the range safety officer destroyed them. The crew compartment, human remains, and many other fragments from the shuttle were recovered from the ocean floor after a 3-month search and recovery operation. The exact timing of the deaths of the crew is unknown, but several crew members are thought to have survived the initial breakup of the spacecraft. The orbiter had no escape system, and the impact of the crew compartment at terminal velocity with the ocean surface was too violent to be survivable. The disaster resulted in a 32-month hiatus in the Space Shuttle program. President Ronald Reagan created the Rogers Commission to investigate the accident. The commission criticized NASA's organizational culture and decision-making processes that had contributed to the accident. Test data since 1977 demonstrated a potentially catastrophic flaw in the SRB's O-rings, but neither NASA nor SRB manufacturer Morton Thiokol had addressed this known defect. NASA managers also disregarded engineers' warnings about the dangers of launching in cold temperatures and did not report these technical concerns to their superiors. As a result of this disaster, NASA established the Office of Safety, Reliability, and Quality Assurance, and arranged for deployment of commercial satellites from expendable launch vehicles rather than from a crewed orbiter. To replace Challenger, the construction of a new Space Shuttle orbiter, Endeavour, was approved in 1987, and the new orbiter first flew in 1992. Subsequent missions were launched with redesigned SRBs and their crews wore pressurized suits during ascent and reentry. Background, edit. Space Shuttle, edit. Main article, Space Shuttle. The Space Shuttle was a partially reusable spacecraft operated by the U.S. National Aeronautics and Space Administration, NASA. It flew for the first time in April 1981, and was used to conduct in-orbit research, and deploy commercial, military, and scientific payloads. At launch, it consisted of the orbiter, which contained the crew and payload, the external tank, ET, and the 2 solid rocket boosters, SRBs. The orbiter was a reusable, winged vehicle that launched vertically and landed as a glider. 5 orbiters were built during the Space Shuttle program. Challenger, of 099, was the second orbiter constructed after its conversion from a structural test article. The orbiter contained the crew compartment, where the crew predominantly lived and worked throughout a mission. 3 Space Shuttle main engines, SSMEs, were mounted at the aft end of the orbiter and provided thrust during launch. Once in space, the crew maneuvered using the 2 smaller, aft-mounted Orbital Maneuvering System, OMS, engines. When it launched, the orbiter was connected to the ET, which held the fuel for the SSMEs. The ET consisted of a larger tank for liquid hydrogen, LH2, and a smaller tank for liquid oxygen, LOX, both of which were required for the SSMEs to operate. After its fuel had been expended, the ET separated from the orbiter and re-entered the atmosphere, where it would break apart during re-entry and its pieces would land in the Indian or Pacific Ocean. 2 solid rocket boosters, SRBs, built by Morton Thiokol at the time of the disaster, provided the majority of thrust at liftoff. They were connected to the external tank, and burned for the first 2 minutes of flight. The SRBs separated from the orbiter once they had expended their fuel and fell into the Atlantic Ocean under a parachute. NASA retrieval teams recovered the SRBs and returned them to the Kennedy Space Center, KSC, where they were disassembled and their components were reused on future flights. Each SRB was constructed in 4 main sections at the factory in Utah and transported to KSC, then assembled in the Vehicle Assembly Building at KSC with 3 tang and clevis field joints, each joint consisting of a tang from the upper segment fitting into the clevis of the lower segment. Each field joint was sealed with 2 20-foot, 6-meter, diameter Viton rubber O-rings around the circumference of the SRB and had a cross-section diameter of 0.280 inches, 7.1 millimeters. The O-rings were required to contain the hot, high-pressure gases produced by the burning solid propellant and allowed for the SRBs to be rated for crewed missions. The 2 O-rings were configured to create a double-bore seal, and the gap between segments was filled with putty. When the motor was running, this configuration was designed to compress air in the gap against the upper O-ring, pressing it against the sealing surfaces of its seat. On the SRB critical items list, the O-rings were listed as criticality 1R, which indicated that an O-ring failure could result in the destruction of the vehicle and loss of life, but it was considered a redundant system due to the secondary O-ring. O-ring concerns, edit. Evaluations of the proposed SRB design in the early 1970s and field joint testing showed that the wide tolerances between the mated parts allowed the O-rings to be extruded from their seats rather than compressed. This extrusion was judged to be acceptable by NASA and Morton Thiokol despite concerns of NASA's engineers. A 1977 test showed that up to 0.052 inches, 1.3 millimeters, of joint rotation occurred during the simulated internal pressure of a launch. Joint rotation, which occurred when the tang and clevis bent away from each other, reduced the pressure on the O-rings, which weakened their seals and made it possible for combustion gases to erode the O-rings. NASA engineers suggested that the field joints should be redesigned to include shims around the O-rings, but they received no response. In 1980, the NASA Verification /Certification Committee requested further tests on joint integrity to include testing in the temperature range of 40 to 90 degrees Fahrenheit, 4 to 32 degrees Celsius, and with only a single O-ring installed. The NASA program managers decided that their current level of testing was sufficient and further testing was not required. In December 1982, the critical items list was updated to indicate that the secondary O-ring could not provide a backup to the primary O-ring, as it would not necessarily form a seal in the event of joint rotation. The O-rings were redesignated as Criticality 1, removing the R to indicate it was no longer considered a redundant system. The first occurrence of in-flight O-ring erosion occurred on the right SRB on STS-2 in November 1981. In August 1984, a post-flight inspection of the left SRB on STS-41D revealed that soot had blown past the primary O-ring and was found in between the O-rings. Although there was no damage to the secondary O-ring, this indicated that the primary O-ring was not creating a reliable seal and was allowing hot gas to pass. The amount of O-ring erosion was insufficient to prevent the O-ring from sealing, and investigators concluded that the soot between the O-rings resulted from non-uniform pressure at the time of ignition. The January 1985 launch of STS-51C was the coldest space shuttle launch to date. The air temperature was 62 degrees Fahrenheit, 17 degrees Celsius, at the time of launch, and the calculated O-ring temperature was 53 degrees Fahrenheit, 12 degrees Celsius. Post-flight analysis revealed erosion in primary O-rings in both SRBs. Morton Thiokol engineers determined that the cold temperatures caused a loss of flexibility in the O-rings that decreased their ability to seal the field joints, which allowed hot gas and soot to flow past the primary O-ring. O-ring erosion occurred on all but one, STS-51J, of the Space Shuttle flights in 1985, and erosion of both the primary and secondary O-rings occurred on STS-51B. To correct the issues with O-ring erosion, engineers at Morton Thiokol, led by Alan MacDonald and Roger Poscioli, proposed a redesigned field joint that introduced a metal lip to limit movement in the joint. They also recommended adding a spacer to provide additional thermal protection and using an O-ring with a larger cross-section. In July 1985, Morton Thiokol ordered redesigned SRB casings, with the intention of using already manufactured casings for the upcoming launches until the redesigned cases were available the following year. Mission, edit. Main article, STS-51L. The Space Shuttle mission, named STS-51L, was the 25th Space Shuttle flight and the 10th flight of Challenger. The crew was announced on the 27th of January, 1985, and was commanded by Dick Scobie. Michael Smith was assigned as the pilot, and the mission specialists were Ellison Onizuka, Judith Resnick, and Ronald McNair. The two payload specialists were Gregory Jarvis, who was assigned to conduct research for the Hughes Aircraft Company, and Krista McAuliffe, who flew as part of the Teacher in Space project. The primary mission of the Challenger crew was to use an inertial upper stage, IUS, to deploy a tracking and data relay satellite, TDRS, named TDRS-B, that would have been part of a constellation to enable constant communication with orbiting spacecraft. The crew also planned to study Halley's Comet as it passed near the Sun, and deploy and retrieve a Spartan satellite. The mission was originally scheduled for July 1985, but was delayed to November and then to January 1986. The mission was scheduled to launch on the 22nd of January, but was delayed until the 28th of January. Decision to launch, edit. The air temperature on the 28th of January was predicted to be a record low for a space shuttle launch. The air temperature was forecast to drop to 18 degrees Fahrenheit, 8 degrees C, overnight before rising to 22 degrees Fahrenheit, 6 degrees C, at 6 a.m. and 26 degrees Fahrenheit, 3 degrees C, at the scheduled launch time of 9:38 a.m. based upon O-ring erosion that had occurred in warmer launches. Morton Thiokol engineers were concerned over the effect the record cold temperatures would have on the seal provided by the SRB O-rings for the launch. Cecil Houston, the manager of the KSC office of the Marshall Space Flight Center, set up a conference call on the evening of the 27th of January to discuss the safety of the launch. Molten vehicle engineers expressed their concerns about the effect of low temperatures on the resilience of the rubber O-rings. As the colder temperatures lowered the elasticity of the rubber O-rings, the engineers feared that the O-rings would not be extruded to form a seal at the time of launch. The engineers argued that they did not have enough data to determine whether the O-rings would seal at temperatures colder than 53 degrees Fahrenheit, 12 degrees Celsius, the coldest launch of the Space Shuttle to date. Molten vehicle employees Robert Lund, the Vice President of Engineering, and Joe Kilminster, the Vice President of the Space Booster Programs, recommended against launching until the temperature was above 53 degrees Fahrenheit, 12 degrees Celsius. The teleconference held a recess to allow for private discussion amongst Molten vehicle management. When it resumed, Molten vehicle leadership had changed their opinion and stated that the evidence presented on the failure of the O-rings was inconclusive and that there was a substantial margin in the event of a failure or erosion. They stated that their decision was to proceed with the launch. Molten vehicle leadership submitted a recommendation for launch, and the teleconference ended. Lawrence Mulloy, the NASA SRB project manager, called Arnold Aldrich, the NASA mission management team leader, to discuss the launch decision and weather concerns, but did not mention the O-ring discussion. The two agreed to proceed with the launch. An overnight measurement taken by the KSC ICE team recorded the left SRB was 25 degrees Fahrenheit, 4 degrees C, and the right SRB was 8 degrees Fahrenheit, 13 degrees C. These measurements were recorded for engineering data and not reported, because the temperature of the SRBs was not part of the launch commit criteria. In addition to its effect on the O-rings, the cold temperatures caused ice to form on the fixed surface structure. To keep pipes from freezing, water was slowly run from the system. It could not be entirely drained because of the upcoming launch. As a result, ice formed from 240 feet, 73 m, down in the freezing temperatures. Engineers at Rockwell International, which manufactured the orbiter, were concerned that ice would be violently thrown during launch and could potentially damage the orbiter's thermal protection system or be aspirated into one of the engines. Rocco Petrone, the head of Rockwell's Space Transportation Division, and his team determined that the potential damage from ice made the mission unsafe to fly. Arnold Aldrich consulted with engineers at KSC and the Johnson Space Center, JSC, who advised him that ice did not threaten the safety of the orbiter, and he decided to proceed with the launch. The launch was delayed for an additional hour to allow more ice to melt. The ice team performed an inspection at T20 minutes which indicated that the ice was melting, and Challenger was cleared to launch at 11:38 a.m. East, with an air temperature of 36 degrees Fahrenheit, 2 degrees Celsius. Launch and failure, edit. Further information, timeline of the STS-51L mission. Liftoff and initial ascent, edit. At T+0, Challenger launched from the Kennedy Space Center Launch Complex 39B, LC-39B, at 11:38 a.m. beginning at T+0.678 until T+3.375 seconds. 9 puffs of dark gray smoke were recorded escaping from the right-hand SRB near the aft strut that attached the booster to the ET. It was later determined that these smoke puffs were caused by joint rotation in the aft field joint of the right-hand SRB at ignition. The cold temperature in the joint had prevented the O-rings from creating a seal. Rainfall from the preceding time on the launch pad had likely accumulated within the field joint, further compromising the sealing capability of the O-rings. As a result, hot gas was able to travel past the O-rings and erode them. Molten aluminum oxides from the burned propellant resealed the joint and created a temporary barrier against further hot gas and flame escaping through the field joint. The Space Shuttle main engines, SSMEs, were throttled down as scheduled for maximum dynamic pressure, max Q. During its ascent, the Space Shuttle encountered wind shear conditions beginning at T+37, but they were within design limits of the vehicle and were countered by the guidance system. Plume, edit. At T+58.788, a tracking film camera captured the beginnings of a plume near the aft-attach strut on the right SRB, right before the vehicle passed through max Q at T+59.000. The high aerodynamic forces and wind shear likely broke the aluminum oxide seal that had replaced eroded O-rings, allowing the flame to burn through the joint. Within 1 second from when it was first recorded, the plume became well defined, and the enlarging hole caused a drop in internal pressure in the right SRB. A leak had begun in the liquid hydrogen, LH2, tank of the ET at T+64.660, as indicated by the changing shape of the plume. The SSMEs pivoted to compensate for the booster burn-through, which was creating an unexpected thrust on the vehicle. The pressure in the external LH2 tank began to drop at T+66.764, indicating that the flame had burned from the SRB into the tank. The crew and flight controllers made no indication they were aware of the vehicle and flight anomalies. At T+68, the captain, Richard O'Covey, told the crew, "Challenger, go at throttle up," indicating that the SSMEs had throttled up to 104% thrust. In response to Covey, Scobie said, "Roger, go at throttle up." This was the last communication from Challenger on the air-to-ground loop. Vehicle breakup, edit. At T+72.284, the right SRB pulled away from the aft strut that attached it to the ET, causing lateral acceleration that was felt by the crew. At the same time, pressure in the LH2 tank began dropping. Pilot Mike Smith said "oh," which was the last crew comment recorded. At T+73.124, white vapor was seen flowing away from the ET, after which the aft dome of the LH2 tank fell off. The resulting release of all liquid hydrogen in the tank pushed the LH2 tank forward into the liquid oxygen, LOX, tank with a force equating to roughly 3 million pounds force, 13 meganewtons, while the right SRB collided with the intertank structure. These events resulted in an abrupt change to the shuttle stack's attitude and direction, which was shrouded from view by the vaporized contents of the now destroyed ET. As it traveled at Mach 1.92, Challenger took aerodynamic forces it was not designed to withstand and broke into several large pieces: a wing, the, still firing, main engines, the crew cabin, and hypergolic fuel leaking from the ruptured reaction control system were among the parts identified exiting the vapor cloud. The disaster unfolded at an altitude of 46,000 feet, 14 kilometers. Both SRBs survived the breakup of the shuttle stack and continued flying, now unguided by the attitude and trajectory control of their mothership, until their flight termination systems were activated at T+110. Post-breakup flight controller dialog, edit. At T+73.191, there was a burst of static on the air-to-ground loop as the vehicle broke up, which was later attributed to ground-based radios searching for a signal from the destroyed spacecraft. NASA Public Affairs Officer Steve Nesbitt was initially unaware of the explosion and continued to read out flight information. At T+89, after video of the explosion was seen in mission control, the ground control officer reported negative contact and loss of downlink as they were no longer receiving transmissions from Challenger. Nesbitt stated, "Flight controllers here are looking very carefully at the situation. Obviously a major malfunction. We have no downlink. Soon afterwards, he said, we have a report from the flight dynamics officer that the vehicle has exploded. The flight director confirms that. We are looking at checking with the recovery forces to see what can be done at this point. In mission control, Flight Director Jay Green ordered that contingency procedures be put into effect, which included locking the doors, shutting down telephone communications, and freezing computer terminals to collect data from them. Cause and time of death, edit. The crew cabin, which was made of reinforced aluminum, separated in one piece from the rest of the orbiter. It then traveled in a ballistic arc, reaching the apogee of 65,000 feet, 20 kilometers, approximately 25 seconds after the explosion. At the time of separation, the maximum acceleration is estimated to have been between 12 and 20 times that of gravity, g. Within 2 seconds it had dropped below 4g, and within 10 seconds the cabin was in free fall. The forces involved at this stage were probably insufficient to cause major injury to the crew. At least some of the crew were alive and conscious after the breakup, as personal egress air packs, PEAPs, were activated for Smith and 2 unidentified crew members, but not for Scobie. The PEAPs were not intended for in-flight use, and the astronauts never trained with them for an in-flight emergency. The location of Smith's activation switch, on the back side of his seat, indicated that either Resnick or Onizuka likely activated it for him. Investigators found their remaining unused air supply consistent with the expected consumption during the post-breakup trajectory. While analyzing the wreckage, investigators discovered that several electrical system switches on Smith's right-hand panel had been moved from their usual launch positions. The switches had lever locks on top of them that must be pulled out before the switch could be moved. Later tests established that neither the force of the explosion nor the impact with the ocean could have moved them, indicating that Smith made the switch changes, presumably in a futile attempt to restore electrical power to the cockpit after the crew cabin detached from the rest of the orbiter. On the 28th of July, 1986, NASA's Associate Administrator for Space Flight, former astronaut Richard H. Truly, released a report on the deaths of the crew from physician and Skylab 2 astronaut Joseph P. Kewin. The findings are inconclusive. The impact of the crew compartment with the ocean surface was so violent that evidence of damage occurring in the seconds which followed the disintegration was masked. Our final conclusions are: 1. The cause of death of the Challenger astronauts cannot be positively determined. 2. The forces to which the crew were exposed during orbiter breakup were probably not sufficient to cause death or serious injury, and 3. The crew possibly, but not certainly, lost consciousness in the seconds following orbiter breakup due to in-flight loss of crew module pressure. Pressurization could have enabled consciousness for the entire fall until impact. The crew cabin hit the ocean surface at 207 miles per hour, 333 kilometers per hour, approximately 2 minutes and 45 seconds after breakup. The estimated deceleration was 200 g, far exceeding structural limits of the crew compartment or crew survivability levels. The mid-deck floor had not suffered buckling or tearing, as would result from a rapid decompression, but stowed equipment showed damage consistent with decompression, and debris was embedded between the 2 forward windows that may have caused a loss of pressure. Impact damage to the crew cabin was severe enough that it could not be determined whether the crew cabin had previously been damaged enough to lose pressurization. Prospect of crew escape, edit. Further information, shuttle ejection escape systems, post-Challenger abort enhancements. Unlike other spacecraft, the Space Shuttle did not allow for crew escape during powered flight. Launch escape systems had been considered during development, but NASA's conclusion was that the space shuttle's expected high reliability would preclude the need for one. Modified SR-71 Blackbird ejection seats and full pressure suits were used for the two-person crews on the first 4 Space Shuttle orbital test flights, but they were disabled and later removed for the operational flights. Escape options for the operational flights were considered but not implemented due to their complexity, high cost, and heavy weight. After the disaster, a system was